We have talked about ionic bonds. We have talked about metallic bonds. That leaves one. Covalent bonds and Lewis structures. Covalent bonds are formed in a very different way. Ionic bonds are going to be positives and negatives attracting. Metallic bonds are the whole sea of electrons thing. And now covalent bonds in which we share electrons between atoms. So this is going to be some definitions, just basic covalent bonding definitions, but then we're also going to have a pretty good lesson here on Lewis structures and how to draw them. This is one thing where Mr. Wolf and I do very greatly in the method by which we teach how to draw Lewis structures. So this may be something that if you had Mr. Wolf for general chemistry, we may want to talk about this in class tomorrow. So definitely, let me know, and anything else that I need to do to help you out, I will do so. All right, so moving on. So we know that there is a continuum. It's like a rainbow. As you go from red to orange to yellow, can you actually tell where red ends and orange begins, or does it just kind of fade into each other? Right, it just kind of fades in. And that's how ionic and covalent bonds are related. They fade into each other. So in the picture here, you can see that here at the bottom, I have a fully positive and a fully negative thing. That is, follow the purple arrow, 0 electron sharing, and that's an ionic bond. But you can have unequal sharing, and that's the picture in the middle. So you can see a little symbol here. It's like a figure 8 that doesn't quite get completed, and that symbol means partial. It's actually the lowercase letter delta in the Greek alphabet. So it means partial positive and partial negative. And so if you see here, there appears to be some sharing, but it's kind of lopsided still. So following the green arrow, it's unequal sharing, which is considered a polar covalent bond. And then as you see A, you can see that it's very, very uniform as shown, and that is, as the red arrow says, equal sharing or a nonpolar covalent bond. What this is showing, these blue blobs are basically showing what's called electron density, that you have electrons here that are sort of equally dense all over the place, and these black dots would be the cores, the nuclei of these atoms. Here you can see there's a higher density of electrons over on this side versus this side, but there is some electron density in the middle. And here you see no electron density in the middle, meaning there's no sharing happening at all. So quick overview. That's the difference between what we're talking about. So we've already done ionic. Now it's time for covalent. So how do they form? Well, first, excuse me. The attractions that actually hold the bond together result from the electrons and the nucleus actually being attracted to each other. What's going to happen is as you begin to bring two atoms together to try to bond them covalently like this, they're going to begin to show a decrease in potential energy. A lot of this has to do with potential and kinetic energy. So remember, kinetic energy is motion. If you want to bond two atoms together, do you think that once they come together that they should be moving really fast? Probably not, because they might not stick together. So if you decrease potential energy, you are actually increasing kinetic energy. So it says once the atoms get close enough, the potential energy will reach a minimum value, and then it will increase, meaning that think of two atoms coming together, and the closer they get, they start to attract to each other. But if they get too close, the electrons in their energy levels will start to repel each other and begin to push each other away. So we know that potential and kinetic energy are related. So if potential energy is reaching a minimum and then increasing, kinetic is reaching a maximum and then decreasing. Distance between the nuclei at the minimum energy is called bond length. So basically the bond length is how tightly the two atoms are held together. Normal distance between two nuclei in a molecule. Remember, we talked about bond length with covalent bonds before, that it was a covalent radius, and it was actually from nuclei to nuclei measured and then chopped in half. So the lowest kinetic energy is going to be the most favorable for bonds, because you don't want to have two atoms pushing away from each other because they would fly apart. So lowest kinetic energy, most favorable for bonds, and it factors in that whole thing about chemistry favoring stability and everything else in between. If we want to break a covalent bond, we've got to put some energy in. Breaking a bond requires us to do something. Think about a bond being like a board and you want to break it, so we're going to karate chop it. Well, you got to have some energy to karate chop a board in half, and that's really what breaking a covalent bond actually is. So there is a specific amount of energy that is going to be required to do this. It's called bond dissociation energy. Hopefully that word dissociation is one that you're familiar with. To dissociate means to separate. So it's like bond separation energy. And the larger the bond dissociation energy means the more energy is required to break the bond, and it's hence a stronger bond. So we'll talk a whole lot about that as we continue on into later chapters. Basically, we'll relate it to bond strength of, say, single, double, triple bonds, things like that. And we'll do some calculations with bond dissociation energy also. So no calculations with it right now. Just know the definition. To break a covalent bond, it's called bond dissociation energy. So what we really want to focus on today, besides just some of the basic ideas about what it means to be a covalent bond, is Lewis structures and actually drawing Lewis structures. So this is just kind of a simple one to put together. So you can see that on the left side I've got two hydrogen atoms. The little dot would be the electron, so they at least have that one valence electron. And then after the first arrow, you can see that there are these two valence electrons that are held between the two hydrogens. And then after the second arrow, I've removed the two dots and replaced them with a dash. And this is all stuff that should be familiar to you, that a dash means a bond, and a bond is two electrons. So what we have here is a nonpolar covalent bond because the two electrons are shared equally between two atoms, and they are hence then, as it says, spending an equal amount of time around each atom. So if you go back to the original picture that we were talking about, it's the one that has that equal electron density around all of them, a very balanced look. And nonpolar covalent bonds obviously happen between two of the same atoms, but they can happen between two different atoms. Like for instance, when carbon and hydrogen bond, I believe carbon's electronegativity is a 2.5 and hydrogen is a 2.1. So they do have a little electronegativity difference, but that's actually considered to be a nonpolar bond. So just FYI, carbon-hydrogen, nonpolar bond. So another way to show you, or a different example here would be, how about fluorine? So you can see my atoms have 7 valence electrons around each fluorine atom. And then after the arrow, I'm showing you that I've bonded those together. So you can see that there are these 2 electrons in the middle, which are called a shared pair. And then any of the electrons that are not directly in the middle of the 2 atoms are considered an unshared pair, which we begin to call lone pairs. So it's all alone on one of the atoms. They're not shared. So just get used to that terminology: lone pair, shared pair, etc. So that's just some basics with Lewis structures, and I think you can kind of see in each of these examples with the hydrogen and the fluorine that you could imagine just sort of taking this thing here and taking this thing here and just bringing them together, and they sort of naturally fit perfectly. And that's basically how Mr. Wolf tends to teach it. At this stage, it makes it relatively straightforward, but it does become a little bit more difficult, which is why I teach it a slightly different way. So again, I'll get to that in just a second. Before we get into drawing complete structures, I want to have a quick talk with you about something called a coordinate covalent bond. This is likely something that's new that maybe you haven't heard of before. At least in my classes, I know that's the case. So think of it this way, okay? In the 2 examples I just showed you, hydrogen gas and fluorine gas, do you agree both atoms donated an electron to be shared in the bond? Okay, both atoms donated an electron to be shared in the bond. So that was donated by that one was donated, and that they share the bond. This was donated and that was donated, so each atom donated an electron. That's a regular old covalent bond. Well, a coordinate covalent bond is a bond in which both of the electrons for the bond are actually donated by just one atom. And an example of this would be if I wanted to bond a hydrogen ion with the ammonia molecule here. And that would form this polyatomic compound, which you know is called ammonium. Very good. So notice here that the hydrogen has nothing to donate. It has no electrons at all. And the nitrogen has actually 2 electrons that it can donate to the bond. So the final Lewis structure just looks like this, with just single bonds between all nitrogens and hydrogens. The big square brackets here with the positive charge to show that I actually know how to count. What I want you to be clear about is that there is no difference in the way that this type of bond is shown. And that's something that's going to be, I think, different for you if you came from Mr. Wolf's class. These are formed in a different way, but they aren't shown on paper any differently. And so you need to start to make a couple of changes in the way that you're drawing your Lewis structures, because in the way that I'm going to teach you, it's actually much more understandable to one of the graders of the AP test. So we're going to start making some changes. And this is going to be really just one of the biggest ones that's going to come up. So please understand, there's really no difference. It's still a covalent bond. The fact that it's called a coordinate covalent bond honestly does not even matter at this point. You just need to understand that it's just a regular old covalent bond. Okay. Only difference, how it forms. So if we're going to draw Lewis structures, really the first thing that we need to know is what to put in the middle. Because what we want to do is create a skeleton structure. And a skeleton structure is like a skeleton, just bare bones. So you know what atoms you want to put together, and generally there's going to be a central atom in the middle that everything else is going to hang off of. And so to start with drawing Lewis structures, one of the first things is to know, what do I put in the middle? So I have some rules to live by that help you decide on what the central atom should be if you're trying to create a Lewis structure. And you're going to love the first rule. The first rule for deciding what to put in the center is very simple. It's carbon. If you have carbon in your chemical compound, carbon is almost always a central atom. It's in part because it's got 4 valence electrons, and so it can really attach to about anything. So if you have carbon, it's probably carbon. What if you don't have carbon? Well, it's probably the single atom. If you look at your chemical structure or your chemical compound, you may have multiple atoms of this or that, but maybe you only have 1 sulfur, or maybe you only have 1 oxygen, and that might be the middle atom, the central atom. So if you can't get to that, then maybe it's the atom listed first. It is possible that you could have 2 of the same atom share central atom duties. In fact, it's almost like like if you had C2H2. I'm probably not going to put the hydrogens in the middle. I'm probably going to put the carbons in the middle, and they can kind of share that whole middle duty. And I'll show a few things that deal with that here in a little bit. Fourth rule to live by, it's the least electronegative atom. So if you had to choose between putting fluorine or sulfur as a central atom, which one would you choose? I hope you said sulfur, because sulfur is less electronegative than fluorine. This works because basically the more electronegative you are, the less willing you are to share your electrons. You want your electrons for yourself. You're really good at attracting them to yourself, and you're not going to let anybody mess with you. So fluorine will not be a central atom ever, because it's too greedy, is I guess the easiest way to put it. So least electronegative atom. And the final rule is it's never hydrogen. You cannot put hydrogen as a central atom because hydrogen fills with 2 electrons. Because hydrogen fills with 2, it doesn't make sense to put it in the middle because you can only put 1 thing on the hydrogen. So hydrogen never goes in the middle. So the big thing I want you to recognize about these rules to live by that are on the screen now is that it's sort of a progressive list. Like you start at number 1. It's carbon. Okay, if you don't have carbon, then move to rule 2. Okay, it's a single atom. Well, what if I have 2 single atoms? Okay, we'll move to rule number 3. And then it's the atom listed first. Okay, well, let's verify rule 4. Is the atom listed first the least electronegative? Basically, if you can fulfill as many of these rules as possible, you've made a correct choice on your central atom. And what I would tell you is that as we move through the rest of this presentation, don't forget these rules, because it's really with the homework that you're going to utilize these rules very, very, very well. So keep these rules in mind. And then as I go through an example, we won't necessarily be using these rules in my example, but these rules are incredibly important. Do you get that? They're incredibly important. Okay, so moving on. Example. So this is the steps that I like to work with when we do a Lewis structure. So I want to draw a Lewis structure for oxygen gas, O2. So the first thing that I'm going to do is I'm going to ask myself the question, okay, well, how many of each atom are there? Okay, well, it's O2, so hopefully you agree with me that I have 2 oxygens. Second question, how many total valence electrons are there? Okay, well, each oxygen has 6 valence electrons, and I have 2 oxygen atoms, so 6 times 2 is 12 total electrons that when I finish my structure have to be on it. So 12 electrons between 2 oxygens. Next, I'm going to draw the skeleton structure. And the skeleton structure, like I said before, is bare bones. So this is where you would really utilize your central atom rules. This is when you think about, okay, is it carbon I put in the middle? Is it a sulfur I put in the middle? This is where you utilize those rules from the last page. And the skeleton structure, to be bare bones, requires at least a single bond attachment. So in the case of my example here, it's relatively straightforward. I have 2 oxygens. I can't really do anything else but put a bond between them, and voila, you've got your skeleton structure. If it's something like CH4, you would probably put the carbon in the middle and then attach 4 of your hydrogens with single bonds around it. So draw a skeleton structure, attaching everything with single bonds and using your central atom rules. Next, you will do some counting. So how many electrons have I placed and how many are left to place? And then once you know, put them on there already. So this is what I've created already. I've got my skeleton structure, 2 oxygens single bonded together, and we recognize that 1 dash equals 2 electrons. Well, I needed 12, didn't I? So if I needed 12 and I've placed 2, that means I've got 10 left. All right, so now I'm on to the next part here, the put them on already. So I've got 10 to go. Okay, your first rule is fill the octet of the central atom first. Now, in this case, with this example, I don't actually have a central atom, by itself. So it's a little tricky to do A right now, but that's a really key point. Fill the octet of the central atom first. Next, place the rest of the electrons around the other atoms and try to tweet twins the same. That's really hard to say. You should try to say it. You should pause the video right now and try to say that. Try to treat twins the same. Okay, so what do I mean by that? Well, are the 2 oxygen atoms that I have on my skeleton structure twins? Yeah. So I want to treat them the same. It means I want to try to give them the same amount of electrons if I can. But additionally, I also have to place electrons in pairs. I cannot single my electrons out at this point. So what I'm going to do is this. I'm going to put 2 electrons on this guy. And then I'm going to put 2 electrons on that guy. Okay, this is me treating twins the same. Then I'm going to put 2 there, and I'm going to put 2 there. Now notice how many I put on so far. 2, 4, 6, 8. And remember, I had 10 left, so I've got 2 more. Well, this is the part where now I have to use Rule C, place electrons in pairs. So I'm just going to pick an oxygen and give it the electrons. And this is fulfillment of number 4. Okay, so I have 12 electrons on there, but I'm not done yet. Okay, Rule 5. Who's happy, which means a stable octet, and who's not? So this is what I just created. Who's happy? Okay, is he happy? I hope you said yes. And he's happy, oh yeah, because he's got 8 electrons. So he's got 2 electrons that are wrapped up in the bond, and then he's got another 6 here that he has for himself. So he's a happy guy. He's got his octet. What about that guy? Boo, hiss. No, he's not happy. The 2 electrons shared in the bond count for everybody. So notice that I've created basically a Venn diagram right here. So anything that's in the middle is shared between both, and it counts for both. So these 2 electrons count as the octet for the guy on the right, but they also count for the octet for the guy on the left. So this guy's only got 6, not happy. Not happy at all. Now, if everybody is happy, which of course in this case they're not, if everybody is happy, you're done. You've created your structure and you're good to go. But if everybody is not happy, now you need to do number 6, which is move electron pairs to make each atom happy. And by happy, I mean stable, I mean octet. So if there is a happy one, it must share first. So in the case of what we have here, we do have a happy guy, and that's this guy here. So those 2 electrons need to be shared, which means they have to go into the middle, right? So that creates this. So you can see that I now have a double bond in between my 2 oxygens. And basically my next step is, okay, who's happy, who's not? Every time you move an electron pair, and by the way, you have to move them in pairs. Every time you move an electron pair, then go back to step 5. Who's happy, who's not? Once everybody's happy, you're done. But if everybody's not happy, you'll have to move electron pairs again. So in this case, when you look at it with the whole, circles and Venn diagram and everything, you can see that this guy has 8, and now that guy got 8, and now everybody's happy. And we say, woohoo. So those are the steps. Now again, in this example, it's a little bit of a simplistic example, but if you go back and follow those rules for central atom and go through these 6 steps, you will be able to get this down and it won't be too difficult at all. So before we go on to a couple of examples for you guys to try on your own, I have a couple other tips. For instance, tip 1, most atoms will follow the octet rule. They will sometimes be forced to form double or triple bonds to do this, but they will follow the octet rule. There will be a few, let's see, it'll be in the next video lesson, that will be exceptions to the octet rule, but the majority of atoms follow it. Just so you're also aware, double bonds will usually form with the atoms listed here: carbon, nitrogen, oxygen, sulfur. So if you need to form a double bond, definitely form it with these 4 atoms. They tend to form double bonds quite readily, whereas triple bonds only tend to form with carbons and nitrogens. So these are just things to keep in mind as you're creating structures. If you start putting double bonds between chlorines, it's probably not right. If you try to put a triple bond with sulfurs and oxygens, it's probably not right. So just, again, things to keep in mind. Carbons and nitrogens will tend to form triple bonds. Almost anything else really will not. So, helpful hint. Try to make it look visually even. Try to make your structure look balanced. If your structure has a visual on paper look of balance, it's probably right. I know that seems like a very simplified explanation or exclamation. I think that's the right word. Explanation. No, explanation. I think that's an overly simplistic explanation for how to determine if your structure is right or not. But I promise you, it actually works. So trust me. And then again, treat twins the same if possible. And if you have triplets, if you have 3 oxygens, 4 hydrogens, try to treat these twins, triplets, quadruplets the same if possible. Because again, in general, that's going to create a balanced look to the structure. It's going to make you put double and triple bonds in the appropriate places. And again, it's a pretty easy rule, but it ends up working out actually quite a lot. So those tips should help you as you move into homework as we come back to class tomorrow. So the final thing that I have for you is a few examples for you guys to actually try right now on your own. So what I ask is that you try to draw the following molecules using the central atom rules on the previous slides and the steps that I gave you. Please take a moment, try these 4, pause the video, and then I'll show you the answers when you come back. Okay, so you have tried them. I'm hoping that you have something on paper, and I'm hoping that for C2H4 you made this. Maybe not at those angles that I have, but that's okay. I'm hoping for C2H2 you might have made a triple bond. I'm hoping for CO2 you might have something that looks like this. So again, we're treating twins the same there, the O's being treated the same. And for NOF, I'm hoping you did this. So this is probably the most interesting one to talk about because you had to really use central atom rules. First off, it's carbon. There's no carbon. Okay, so it's a single atom. Yeah, I got 3 of those. Okay, so it's the thing listed first. Okay, so it's nitrogen. Okay, let's check rule 4. It's the least electronegative. Ooh, it actually is. Nitrogen is more or less, electronegative than oxygen and fluorine, so it makes more sense to put the nitrogen in the middle. Now, you'll also notice that there was the choice of putting a double bond either on the oxygen or fluorine. Well, go back to what we talked about on the previous slide. Double bonds primarily form between carbons, nitrogens, oxygens, and sulfurs. And notice fluorine's not on that list. Fluorine is greedy. Fluorine wants all of the electrons it can have to itself and not share if possible. So in this case, fluorine has to share 2, but if you want to try to make it share anymore, it's going to put up a fight. So the double bond really needs to be put between the oxygen and the nitrogen to be correct, and that's because of electronegativities and also general behaviors. So hopefully you're able to figure those ones out, and when you come back to class tomorrow, we'll do some more practice. Yay! And that's it. So exciting.